Good morning, everyone. As Lynn said, I'm Mark Walker, and I'm talking to you today on behalf of myself and my colleagues at Manly, Artem Tuntsov and Arthur Suvorov. And for those of you who haven't been to Sydney, that's the picture up there. It's Manly. So I don't come from a stellar background. I work on the interstellar medium, so I'm very much a novice. And this week has been very interesting indeed, but also a bit of overload in terms of all of the new stuff that I've been learning. So the R Cor Borealis stars, probably most of you know more about them than I do. I'll just give you a quick sketch of the essential features. There's a lot you could say, but for the purposes of this talk, the key things to know are that they're supergiants. Most of them are cool. There are some hot ones. Most of them are cool, but unusually, very hydrogen deficient objects and very carbon rich objects. But their truly outstanding characteristic, the defining characteristic really, is that they experience these random fading events where they'll suddenly drop in brightness over a matter of weeks to months by a factor of 100 or even 1,000 or maybe more. And Consequently will show you more data in the talk after this one and go into more details there, exactly what they look like. But here's a couple of examples of fading events shown here over a period of a bit more than 3 years and 10 magnitudes on the vertical scale. So just imprint that general impression if you're not familiar with the data on your mind, because I'll show you some models soon that are on the same format, so same duration and same magnitude scale. A key point is that the dust sprays that, oh yes, I didn't say the fading events are due to dust extinction, and those dust sprays that emerge are known to be highly anisotropic. They're not all over the sphere. Okay, so how do you understand how these understood? They are R Cor Borealis stars in the conventional picture. Well, they're helium supergiants, as I just said. And so the picture there is of a degenerate CO core with an extended helium envelope. And at the base of that envelope, you're burning the helium to carbon. And with a bit of luck, you can dredge that carbon up into the envelope, and then you get carbon-rich feature. So models will go back to Trimble, at least to Trimble and Pajinski, probably before that also, and then Ivan and Tutikov in 1989 and so on. So the dominant idea about how these stars evolve, how do they arise, is that you start off with two white dwarfs, one helium white dwarf and one CO white dwarf. You merge them, and then the dense CO white dwarf ends up with the helium white dwarf essentially as an envelope. And then again, the conventional idea is that the fading events are due to carbon dust being ejected from the star and then continuing its journey outwards. And so the dust optical depth decreases and the star gradually recovers. And that idea goes back to a long way now. But despite the fact that the idea has been around for a long time, there is actually no model. There's no quantitative physical model for that behavior, of the fading events. Okay, so that's that should give you cause for concern, because it probably means it's very difficult to model. But let me give you a bit more motivation for why that interpretation may be problematic. So here's an observation from Jeffers in 2012, imaging polarimetry of R Cor Bor during minimum. So the star has practically disappeared. Here you can see there it is. And this thing here is a dust cloud that's been ejected perhaps half a century ago. And you can make a rough estimate of the mass of that cloud, the mass of dust in that cloud. And the mass is about 3 × 10⁻⁴ with a large error bar, but still that's the number. And that amounts to pretty much all the carbon that you have in the stellar envelope. So that's a problem. So in this talk, I'm going to talk to you about an idea that instead of the star producing the dust is actually brought into the picture by a second body. And that body is just a gas cloud, a dusty gas cloud, and in fact, a hydrogen snow cloud. So what I mean by that, or hydrogen snow cloud, I mean that the gas cloud is very cold and very dense, and so hydrogen can actually precipitate, condense into solid form. So the cloud is full of very, very tiny particles of solid hydrogen, sort of drifting gradually down to the center under gravity and being stirred up by convective motions. So that's the sort of picture you can imagine. So hydrogen snow clouds first appeared in astronomy really in the mid-90s. Dan Feniger and Francois Combe had the idea that you needed a reservoir of dark gas in order to form stars at the rate you see them in the spiral galaxies. And so they conceived of this reservoir as being full of massive, very massive clouds, self-gravitating and fractal, a bit like the ISM that you sort of can image. But dark, and so not actually in our catalogues, and making a significant contribution to the internal dynamics of galaxies. So subsequently, there was a shift a couple of years later. Gerhard and Silk proposed instead small spherical clouds, and then used that very concrete picture to put a load of constraints on their properties. So there are a lot of constraints, but it's a viable possibility. Oops, too far. Come back. So as an aside, I'll say that if you just think about the idea of having particles of solid hydrogen out there in the ISM, that itself is an interesting idea. So if you look at the properties of the dust, so solid hydrogen is not conventionally thought to be a component of interstellar dust. And the reason is that if you just have pure solid hydrogen, a micron-sized particle will sublimate in a matter of months. So if you were to make some, it would be gone almost straight away, so it can't be relevant. That was the idea. And that's been around since the late 60s. But that is a very misleading idea, because when in the ISM, grains charge up, and the electric fields associated with charges stabilize these grains. Okay, so actually they can be, so they can live essentially indefinitely in benign areas of the ISM. So that's a reason to take it seriously. And it also turns out that charged H2 grains, again because of the electric fields, are spectroscopically very rich. So there are counterparts for most of the mid-infrared bands, the bands that are usually called the PAH bands. There's also a line at 9.6 micron. So at this point, you ought to be getting very worried as to whether or not you have the right picture of interstellar dust. And it turns out there are hundreds of weak optical transitions. So I'd like to get people thinking about the possibility that those are the diffuse interstellar bands. So that's an aside, enough about interstellar medium. So what should you think of when you're imagining a hydrogen snow cloud? Mark Wardle and I tried modeling these things. It took us ages, but eventually we got something. The models are not very good, I'll be upfront about that, but radii like planetary orbits. So enormously dense compared to the typical bit of the ISM, but very low density compared to something like a star. And that means that if they come anywhere near a star, they'll be tidally disrupted, which is important later on. Okay, so if you were to bring one of these things near a star, in particular a luminous star like R Cor Bor stars are, what happens? Well, it turns out hydrogen dust is almost entirely scattering in the optical. Its refractive index is almost entirely a real refractive index. And so you would have pressure forces on the grain from light coming directly from the star, which is shown here. But you would also have all the light that's incident on this cloud also eventually has to emerge from the cloud because you're just scattering the photons. And so there's also a lateral pressure from the scattered photons coming back out of the cloud. And so instead of just being driven sort of radially away from the star, they're actually driven out at about 45 degrees. So this is actually a calculation here, not just a kind of graphic. So if I put this thing here at 4 AU away from this very luminous star, this is the sort of thing you get if you look up close. And if you step back a bit and look at the bigger scale, so here's 100 times zoomed out, then of course the orbit of the thing around the star, the this dust tail kind of sweeps back like that. So the wind speeds that you get out in this calculation, when you have 10 to the 4 solar luminosities from your star, are really very high. They're about 1,000 kilometers a second coming off this cloud here. And this model here that I'm showing you, the one I'm using throughout, is one in which that dust wind is infinitely thin. 10 minutes already. Woo. Okay. Okay, so this is my video of which doesn't actually work. It gets to that point and then stops. Sorry about that. And then it jumps to the end. So I'll go on to the next slide. It was a beautiful visualization when it worked properly. So jumping straight to the light curves. So this is the sort of thing we can generate on the same sort of graph scales that I showed you for the data. And this particular case is a cloud whose periastron is at 4 AU. The observer is at the longitude of the periastron, and the latitude above the orbital plane is 20 degrees. And those are the only parameters that enter into this calculation. Essentially, everything else is fixed. There aren't really any other free parameters in here. Maybe the cloud radius. So let me just focus on some points. So things to notice here are the event has a very fast onset. And that's, although this cloud is actually not moving very quickly, it's just in Keplerian motion, but the dust wind extends out to much, much larger radii, and it's the leading edge of that dust wind coming across the star that has a much super Keplerian speed, and so the onset here is very rapid. And by contrast, the recovery is very slow, and that's because you're gradually getting less and less optical depth in the wind as it moves past. And the depth of the event in magnitudes and the duration here similar to what's observed. This thing here, this spike, is nothing like what's in the data, and this is entirely coming out of the thin sheet approximation that we're using to model. So insofar as you can ignore that, just do so, because it's just a calculational artifact. Show you a couple more. So that's one where I bring the cloud in to half the distance, about now down to 2 AU. Not surprisingly, the whole event gets a bit shorter, actually gets a bit deeper too. Pushing it further out lasts a bit longer. This one, actually, you're just grazing the top edge of the dust sheet. And so you have a slightly different morphology. And here the calculational artifact is actually interfering with your ability to see what the structure of the light curve is, because it's sort of merged with the rest of the light curve. So there it's actually a bit of a problem, but for most other purposes it's okay. And here's one where I've pushed it out to 8 AU and then down. The observer's now down closer to the orbital plane, only 10 degrees off. So caveats, we're not explicitly putting in the dust-gas coupling. We haven't put in the scattered light, so it's purely scattering, and we've just the things. So the tidal effects are really important. So you're probably all familiar with this from the context of stars being disrupted by massive black holes in the centers of galaxies. Same sort of thing happens here. In fact, this calculation, or the schematic rather, is taken from that. So it's obviously not to scale, starts off spherical, gets gradually distorted as it comes close to the gravitating object, and then it heads off out, being very elongated like this and disrupted. And this part of the debris actually falls back and is accreted, and this half of the debris is unbound and goes off to infinity. So that's the standard text. And in our case, what happens is that because you're undergoing this very large expansion, and so the material becomes very cold, all of the hydrogen condenses, all of it. And then it all gets blown away by the radiation pressure, providing it's in lumps smaller than about 1 centimeter, so pretty chunky sized lumps. And so what that leaves is just helium to fall back onto the central object. And so in our case now, this is fantastically useful, because the model you're using to give you your fading events actually gives you an evolutionary pathway. So you can start off with something very common, like a white dwarf, and end up with something very rare, like a hydrogen-deficient carbon-rich supergiant. But the key thing remaining is you need to have lots of these events. R Cor Bor shows one of these things every few years. So you need to somehow be disrupting a snow cloud every few years. How do you do that? Well, I think this, from my point of view, this is the least satisfactory, the moment aspect of this model. So the hypothesis I want to work with is that actually stars, all stars, carry halos of these snow clouds, like thousands, tens of thousands of these snow clouds, which might sound completely outrageous, except that you can look in the Helix Nebula and find that it has 40,000 molecular mass, planetary mass molecular gas clouds. So maybe it's not that unreasonable. So a background picture from Makaku Matsura with Subaru. And then all you've got to do, or in inverted commas you've got to do, is you just got to get the white dwarf to traverse this halo. So here's a kind of schematic of the 40,000 snow clouds sitting around a central star. You've somehow got to get a white dwarf to traverse this halo, and then you'll get a huge rate of disruption events and a huge rate of fading events from that system. So possibilities for doing that are to bring a white dwarf in from the outside in a sort of chance encounter. That turns out to be very rare. So it's not an idea that I favor. I think the sensible thing to think about is an inside-out type of traverse where the white dwarf is part of a system down here that the halo clouds is bound to, and then somehow you disrupt that system and send the white dwarf out through the halo. So I would like to do it with a binary, but I think, or at least I haven't been able to make that work yet. And so I had to resort to a triple and wave my hands and say that, the dynamics become chaotic and the triple disrupts. And if you allow me to do that, then this is the sort of thing you can get. So this is an n-body simulation using PyTreeGrav, and I've got a 0.7 solar mass white dwarf and then a pair of main sequence stars in a binary. I disrupt it at time equals 0, and as it goes out through the halo, each of these things disrupts the many gas clouds, and consequently you get a lot of helium accreted onto each one, and the luminosity profiles look something like this for that scenario. And the key thing to note is that I've cheated even more, actually, and I didn't have to just take a helix type distribution, but I actually had to make it much more compact. That's 10 times more smaller in overall radius, this halo, than you see in the helix. But that's the sort of overall scenario. And so key points, first quantitative model of, as far as I know anyway, of R Cor Borealis fading events that gets the depth, durations, and the asymmetry of the events about right. And it also comes with it an evolutionary pathway to go from a white dwarf to a hydrogen-deficient supergiant, which is a strength of the picture. It is, however, at least at present, challenging for us to generate the observed event rate. And so I feel a bit uncomfortable about that scenario that I just showed you. That's definitely the weakest aspect of it. However, I still think the model is overall a very appealing one for a very bizarre phenomenon. And if it's the correct picture, then I think there's no choice but to think that these snow clouds must actually be playing an important role in all the phenomena, circumstellar phenomena that this community is interested in. So I'll stop there. Thank you very much, Lean, for your tolerance.
So why don't we see more types of stars, like more classes, main sequence stars on having these dimmings?
Great question. So so far, the only type of dust wind that we've calculated is the simplest one, which is the one I showed you, and that's where you neglect gravity and the motions of the cloud, and the dust just gets blown out at high speed. So if we were to model an ordinary main sequence star, the luminosities would be vastly lower, and the properties of the dust wind would be very different. My guess, not having done the calculation yet, is that probably the events become very, very long. So the star ends up being, for example, an IR source with little variability. That would be my guess. But I haven't calculated yet, so I can't say with confidence.
Okay, so one of the questions was already asked by Ursula, but I still have two more. So The first is, as far as I recall, and then correct me if I'm wrong, in the standard picture, people usually propose that you have this common envelope event, then you are left with let's say, a closed binary of a CO white dwarf and a helium white dwarf, and this is the thing that merges. So the first question would be, why doesn't this work in your case? And and the other question is, in some way you need to separate the helium from the hydrogen. How does this work?
Okay, so in answer to the first one, I don't know that the scenario doesn't work. It's just that I don't need it. I go from an isolated white dwarf to a helium giant just by accreting helium. And the way the helium and the hydrogen are separated is because the hydrogen condenses into tiny particles, tiny solid particles, and then just like any other dust, it's subject to enormous radiation pressure forces, and it just gets pushed out of the system.
Okay, thanks.
Malcolm.
So would you expect to see any of this like hydrogen snow in our Oort cloud, for example?
That's a great question. I can't say I would expect to. I mean, maybe there is, but you know, my understanding, anybody's understanding of what's required at this point is almost nil. We're kind of groping around in the dark, but it's a possibility.
So what's the best place to look spectrally?
Yeah, I don't know. Right. There are spectral features that I can point you to, but which is the best? I don't know.
And then, Mark, can I still also ask you one basic question? You were saying that the electromagnetic field can stabilize the H2. How does it exactly work? How should I understand the physics?
Yeah, so if you put charges, if you allow if you allow the grain to charge up, as would happen in interstellar space, then you have the electric fields of those charges, and in an electric field, the hydrogen molecule has a lower energy than it does without the electric field. So the polarization energy has to be taken into account if you want to rip the hydrogen molecule off the grain. And it's a factor, it can be a factor of 10 higher than just the van der Waals binding. So it makes a huge difference to the sublimation rate. Yeah.